Okay, back to datums. So we can use planes, points, or axes, lines, to establish datums. We use datums to basically reference from those points. In essence, those points of origin, we can reference other dimensions or tolerance standards from those datums. The datum feature would be the actual datum part itself. So for instance, if we were holding a physical part and using it as a master, and let's say the left plane was to act as the datum, the left plane on the actual part itself would reference the datum feature. We also have datum simulators, and one important and critical datum simulator would be the surface plate. We'll look at that in just a moment. So we're going to be using Pseudemus to establish datums as well. And one thing we'll do is take a part spinning in space and actually lock it down by creating a datum reference frame. In this example, notice that the left, front, and top planes have been established and datums have been assigned to each. What we can do is perform a part alignment and actually align these three datums as one. Their intersection point would be the origin of this part, which is what would most likely be specified on the detailed drawing, hence why we would want to establish that datum reference frame in the first place. So the datum simulator was what I just mentioned to you a moment ago. Notice that since flatness is in essence theoretical, we do our best to achieve as much flatness as possible so that we get most accurate results. If you notice in this case, notice that we have, let's say that we have a fixture here and we're going to gauge a part's tolerances and if acceptable tolerances have been met by using this datum frame here. Notice that the planes of the frame represent the datum feature simulators. The datum features themselves would be the planes that actually touch these frames on the part itself. And we want to see how relatively flat those datum features are compared to that datum feature simulator. Here's an example. If you notice, you can see some CMMs in the back that we'll be working with. This gentleman is inspecting a granite surface plate, like you see here, to make sure that the flatness is within tolerance. Since this is going to be used as a standard for comparison of other measurements, we need to make sure that this holds its accuracy. So let's go back to that flatness for a second. If we look at this a little bit more precisely, notice here's our surface plate. What we want to do if we apply a flatness tolerance is make sure that the part is staying flat within this relative tolerance zone, that no point on the surface is more than 0.2 units, let's say 0.2 millimeters apart. If that constraint has been met, then we know that this flatness constraint has passed. Another important geometric dimensioning and tolerancing characteristic would be circularity or cylindricity. Circularity tests the roundness of a cylinder at different locations. Notice that they don't necessarily need to be circular with respect to each other, but each location must satisfy that roundness tolerance. In this case, our surface must stay within a concentric circle, and that concentric circle references our tolerance zone. In the case of concentricity, or excuse me, my apologies, cylindricity, this is going to be a little bit different because that circularity feature needs to apply to the entire surface of that shaft. So in this case, notice that, as you see here, the cylindricity feature must be constrained so that the entire surface of the cylinder must fall within that concentric circular zone. And that means that the part not only has to have roundness, but also straightness if you think about it, because this waviness may not be permissible for the part's function. Circular runout is another type of GD&T constraint that we'll be talking about, and this is where we might use a tool like a dial indicator and revolve a shaft around an axis and make sure that the dial indicator references what's known as a total indicator reading that doesn't go outside of the tolerance zone stated here. What that means is that the part isn't wobbling or too elliptical where the dial indicator is going up and down too much, evidencing some conditions of us being outside of tolerance for this part's function. We can also look at what's known as total runout. Maybe we don't just care about one specific location. We care about every location along that entire shaft. So in this case, we're going to move our dial indicator across the surface of the shaft while revolving it to make sure that our total indicator reading doesn't go outside of the permissible limits. This allows us to not only check for taper and wobble, we can check for straightness of an axis, we can check for cylindricity, circularity all at once. So looking at total runout, let's think about working in an automotive application where high-speed revolution is critical to the machine's outputs. Making sure that the shaft doesn't have too much taper or wobble and that the axis is straight is a critical constraint in making sure that that part functions properly. So last thing to discuss here before you're put to work is maximum and least material condition. This is an interesting constraint because it allows us to get what's known as bonus tolerance. Maximum material condition is either going to be the largest hole or, the smallest hole or the largest pin that we could create. Think about it. If you haven't machined enough material away, you have the maximum material, which would leave us with the smallest hole. That's the same thing as not machining enough away on a shaft or a pin where there's some more material that hangs around, so the pin would actually be larger. This works in reverse for least material condition, where now you're looking at the smallest shaft or the largest hole size, because now we've machined a lot more material away, so the hole is getting larger and the pin's diameter is getting smaller. RFS is assumed on every document unless the least or maximum material conditions are specified. This used to be a standard that was put on everything in every detailed drawing, and it can make sense why we would want it to be implied because it's going to take up a lot of space on that detailed drawing and really become tough to read what you're trying to read if you've got too many symbols on that drawing. So least and material condition modifiers are really important to us. And the reason why is because if you look at, like, say, for instance, this slot, at least material condition, it's much smaller. But at maximum material condition, as we remove more material away within the specified constraints of our tolerances, what's going to happen here is the slot's a little bigger. Whatever needs to fit inside may have a little bit more wiggle room, so we get what's known as bonus tolerance. And I'll show you how this works. Take a look at this let's say, inch diameter circle that has a diametrical size constraint of 2/1000 of an inch. Remember, that relates to the size of, in this case, the hole. The position of the center of the hole is what's being called out on this feature control frame. Notice that it must fall within a diametrical tolerance of 4/1000 of an inch. So if we could draw a little circle around here, and I'm terrible at drawing circles, but you get the idea, what we would see is that that center must fall within the boundaries set forth by this size circle from its original or true position. Notice that the maximum material condition modifier has been called out. And we are comparing this to 3 datums here. So we're looking at the entire depth of this hole, not just the surface, which we could control with 1 or 2 of these datums. So let's take a look here. Notice that the hole's diameter at maximum material condition would be 0.498. That would be 0.5 minus 0.002. At least material condition, that would be 0.502. Think about that. That would be a larger hole, which means we've machined more away. So these are really the upper and lower boundaries of our size constraint. Now, based on the size of the hole, we'll change how much permissible tolerance we have based on this position constraint. Notice that at maximum material condition, 4/1000 of an inch is our tolerance zone. But if the hole's machined a little larger, we have a little bit more wiggle room. We can take the difference between maximum material condition and the actual material condition and add it to our original tolerance zone, thus giving us bonus tolerance. So as the hole gets larger, whatever pin must fit inside that hole has more wiggle room, which means the center of the hole position has a little bit more wiggle room and can actually move around a little bit more, and that pin will still fit where it needs to fit. Pretty interesting aspect to GD&T. And think about it. We would have to have measured the hole size before we could see if we have any bonus tolerance. Least material condition will work in the same manner. And I'll let you read a little bit more about that or overlook this slide at your leisure. All right, so here's what you're going to be doing. What I'm going to ask you to do is fill in this table to the best of your ability. You're going to be reading section 3, unit 1 to reference detailed drawings and then also learn a little bit more about GD&T. I'm asking you to read that whole unit, which is once again, section 3, unit 1. I'll refer back to that. And to fill in this information, what you're going to do is visit gdntbasics.com. Now, when you come into GD&T Basics, notice that it is a company that's a training company. So they're going to at times give you some information about their training sessions. That doesn't give you any limitations to access to their materials. So what you're going to do is click on GD&T symbols. And let's say if we look back here, our first symbol is straightness. And actually, I'm going to use flatness here. You're going to be filling out all 3 of these tables. If we come back to the flatness constraint, notice that all your symbols are here or located here. You're just going to click on the symbol. And now what you're going to do is read a little bit about what flatness is. You'll also be able to see what the tolerance zone looks like. Notice in this case, it's 2 parallel planes because we make sure that all the points on this plane stay within this parallel plane tolerance zone so that they don't go beyond what's specified in the feature control frame. So if we come over here right off the bat, we can see that in this case, my apologies guys, let me just come back to this chart here and blow it up. If we look here and we come to flatness, one of the questions was, does it need a datum reference? And it doesn't. Notice that relative to datum is no. Here's the symbol that you'll need to call out. This tells you a little bit about your tolerance zone, 2 parallel planes. And the beauty of something like this is that you're going to learn about the practicality of using this constraint. How would we measure a plane to be flat? Well, since we're looking at the entire surface of a plane, it's tough to use a tool that only measures a few points. So a great tool for something like this would be our coordinate measuring machine, our CMM, that could use a probe and actually scan across and pick up many, many points on this entire surface. My apologies. So that's why I want you to take a look at this. It's going to tell you a lot about everything that is that is flatness, and even compare to standard traditional tolerancing methods, why this might be a better method of choice. So you're going to do this for all of these different geometric dimensioning and tolerancing symbols and fill this in. What we're going to do week 3 is start by reviewing to see what you guys have completed, and I can answer any questions that you have. Now, this is something you are going to work on inside of class. That's now become an outside of class assignment. So please do take it seriously. Take your time to read through section 3, unit 1, as well as the gdntbasics.com to help you answer all of these questions. And then we will refer to them together next class. I hope you find this helpful, and I look forward to working with you week 3. So just as a quick to-do, your homework, if I can find it, is going to be, if you look in your week 2 goodies, you can find your week 2 lecture to print out those tables and fill in your notes from this online video. The week 2 homework is assigned. You don't need to read anything to do it. You're picking a measurement article that interests you online, reporting on it, and just make sure that you answer the questions I ask in the assignment and that you type this up and submit electronically through Canvas. All right, I hope this helps, and I look forward to, just once again, really look forward to working with you guys next class.